In this video lesson on calculating electric fields, we're going to return to the charged ring. So we've already seen the example with a complete charged ring. In this one, I'm going to take the charged ring and say, what if there's only a fraction of it? We'll call it an arc of charge. So we get rid of a portion. Let's erase. So the charged object is just a fraction of a full circle or ring of charge. Okay, so we'll take this and make a frame of reference, put it on the x and y axis, and the question becomes, what's the electric field at the center of curvature? So we'll say that this ring carries a total charge Q, and then instead of saying it has a length of L, we'll say its length is S. And it subtends some angle of theta. So we've got it drawn again here a little neater. Now we know for a full circle, circumference is equal to 2 pi multiplied by radius. And that's just a specific case of the more general equation that the distance around any fraction of the circular arc is equal to the angle measured in radians times the radius. So the distance S up to this point is equal to this angle theta multiplied by R. So if we draw it again here, there's R, and there's theta, S equals theta R. Now if we just imagined some small displacement within, so we can say there's this very tiny angle here, just a fraction of the total angle d theta, then the distance taken up along the edge of the arc in this case is just a little fraction ds. And it turns out ds is equal to r times d theta. And again, we'll talk about charge density. In this case, we're back to linear charge density. So the linear charge density we'll assume is constant, and we'll give it that symbol, Greek letter lambda, one more time. So if it's uniform, then if we divide the full arc length, if we divide the total charge Q by the full arc length S, that's the same thing as a little bit of charge that occupies, draw that in again, highlight this space. Okay, so if we highlight this region here, there's just a fraction of the total charge, dq, and right, you get the idea. dq divided by ds is the same density of charge as the total charge q divided by the full arc length s. Now we want to bring some more symmetry into the problem. So let's say we rotate it until this angle and this angle are the same. Okay, so how about we come up with a symbol for this angle? Well, we know from the positive x to the negative x axis has to be 180 degrees, or pi radians. So this angle here that we'll just call what? Phi? Phi must be equal to pi minus theta. Right? We've already defined what we mean by theta. It's this angle. So you get what I'm saying? That means that this angle right here is half of that value. This must be pi minus theta divided by 2, and this is pi minus theta divided by 2. Okay, so we're going to have to count for a little contribution to the total electric field due to that little bit of the charge dq. Then we'll make another slice right here. And it gives a contribution to the overall field. So the first one contributes to the total field in this way. The next one I've shown you contributes to the overall field in this way. We've got another little fraction of the overall charge. There are several of these dq's, another one this way. Well, you can see from the symmetry of it, if I fast forward and we look at another one of these small bits of the total charge dq located over here, its electric field contribution at the point in question is going to be directed this way. So there's going to be some cancellation due to the symmetry. In fact, we should guess that the net amount of electric field along the x-axis is equal to 0, and so the total electric field must really be the summation of all the contributions to the electric field that exist only along the y-axis, right? All of the horizontal components to these vectors will cancel, but there'll be some overall electric field lying along the y-axis. Okay, so dE itself, as we know, is k dq divided by, normally we would say lowercase r squared, but in this case, and this is not arbitrary, generally our approach is to use lowercase symbols for variables and capital symbols for constants, and every one of these little bits of charge, they all have the same distance from the point that we're looking at, right? So we call this capital R. dE is k dq over capital R squared. I'm going to clean this up. Bear with me. Okay, so let's just make sure we know what we're talking about here as far as the direction of these vectors are concerned. At random, we pick one of these elements of charge dq that represents a fraction of the total charge capital Q. It sits at a distance of capital R, and it contributes in part to the overall electric field, some amount dE. And dE is k dq over r squared. However, its x component is going to be canceled out by the x component of some other dq that sits over here. So all we're interested in really is dEy. So we'll say that this bit of charge dq sits at an angle of theta relative to the x-axis. That means this is alternate interior angle, the same value. So dEy represents the opposite side in a right triangle of that defined angle. So this would be dE sine theta. So to get the overall electric field at the point in question, we need to sum up all of our dEy, which means we have to sum up all of our k dq over capital R squared times sine theta. So we'll take constants out of the integral. K divided by capital R squared times the integral of dq sine theta. Now let's think about what varies. Okay, so we picture a different dq. Well, that one sits at a different angle of theta. So as dq changes, theta changes. But as we see, once again, r does not change, right? Which is why we were able to pull it out of the integral. So we want to get this in terms of a single variable. The two obviously relate to one another. Remember, we said that ds is equal to r d theta. And because it's uniform charge density. We also know the ratio of dq over ds is the same as the ratio of the total charge q divided by s. So we make a substitution in step 3 and say our electric field is k over r squared times the integral of q over s times ds. So that's a substitution for dq. We still need to multiply that times sine theta. Now, it would be equivalent, instead of stating q over s as the ratio of charge, we could also just leave that as lambda. So let's do it that way. Let me restate step 3 of this work. Say the electric field is k over r squared times the integral of lambda ds sine theta. Now we need to make another substitution. We still don't have it down to one variable, but this is easy. ds is r d theta. Okay, so our electric field is k lambda over r squared. Right, we've pulled the lambda out of the integral times r sine theta d theta. So we replaced ds with r d theta. And then the r can come out of the integral. So our electric field is k lambda over r times the integral of sine theta d theta. Now, what are our limits of integration? Well, our very first contribution to the overall field comes from this piece of charge. That's initial angle would be the one we defined earlier, right, by changing the symmetry of pi minus theta over 2. And then, of course, our last one has that same angle remaining. However, again, taking advantage of the symmetry of it, instead of making that our upper limit, let's make our upper limit here. We'll pretend that this is the last dq. So that would be at pi over 2, right? And then, in that case, we can just say, oh, by the symmetry of it, we can double the result. So I'm going to throw a 2 in here. Let me color code this. Maybe you review these notes again and realize that that 2 needs an explanation, so we'll make that stand out a little bit. Okay, so upper limit is pi over 2 as long as we include this 2 here. So this means our electric field is 2k lambda over r times cosine of pi minus theta over 2 minus cosine of pi over 2. But of course, cosine of pi over 2 is equal to 0. So we have our final result, 2k lambda over r cosine pi minus theta over 2. Now let's think about what the result would be in the case where it's a full ring. So in other words, I guess we're saying that theta is equal to 2 pi. So we're going to be taking the cosine of pi minus 2 pi divided by 2, which is cosine of negative pi over 2, which is 0. And as we know, for a complete ring, the electric field of the center should be 0. What if we take the case, forgive me for making this sloppy, where we shrink it way down so it's hardly anything at all, so that theta approaches 0. Then we'd be taking the cosine of pi minus 0, pi minus 0 over 2, which again is cosine of pi over 2, which is 0. So the reason it's 0 in this case is different than the full ring. For the full ring, the reason the electric field is 0 at the center is because that little bit of charge and that little bit of charge have electric fields that cancel each other out. This little bit of charge and this little bit of charge cancel each other out. In this case, it's just because we've shrunk it so much, there's hardly any charge at all, right? Because theta is approaching 0, then the total amount of charge, capital Q, is approaching, sorry for spazzing out, is approaching 0. Okay, so always check our results to see if they match the extreme cases, to see if it's valid. And it seems like this is a most likely valid equation. So we're going to settle on that. And once again, say thanks for watching.